We'll see that. Okay, anyway, let us see this triggering pulses properly, whether we can get them or not properly. So if you can connect here, delete, you can go to the wire, select, connect it here, go to the wire, select and connect it here. So these are the switching pulses. Let us use something called mux. Okay. So instead of 10, let us make it as 0.04. Let us run the simulation for 2 cycles. So if I run this, see, it is actually overlapping. So you can choose this, go to layout and select 3 because I have 3 scopes now. Okay. We didn't get it because it is going to give an inverted image. For this, the reference will come with the negative value. So we have to change this reference again by multiplying it with -1. We can type something called gain, give it here, edit it as -1. No, it's not about the comparator. It's about this only. The negative signal is too high. So if you run this, so you may get the thing properly. But if you observe this repeating sequence and this square wave generator are not proper, by default, this switching frequency, whatever the frequency that you use, that was quite less. So before starting the simulation, if you have higher switching frequency operations, here actually it is just 50 hertz. That means 0.02 seconds only. This is what is my frequency. But if my repeating sequence is in the range of 100 kilohertz and all, then it is not going to work. So let us see. Let us make it as 1/50 and let us make t equal to 1e-4, which is 10 kilohertz. If I use such high frequency, I'm not going to get this waveform properly. See, I'm actually getting the waveform irregularly. Actually, I have given a square, triangular wave and square wave, which is not proper now. For that thing, what you have to do is you have to right click anywhere, go to model configuration parameters. In this, you have solver, go to solver details. Make sure the maximum size is something of the order of microseconds. So I'm using 1e-6. It is up to you. If you have megahertz of switching frequency, then you can go for -8 also. But it will take so much time to simulate that range. Only for some microcontroller, how to choose the solver type. The solver type, for most of the electrical applications, we generally use ODE23TB or ODE23T. For some specific like microgrid and all, they will use ODE15S. For majority of solar PV and all, they'll use ODE23TB. So it's up to you. You can choose. If you don't want that, even you can go for discrete solvers also. In order to deploy in hardware, in order to test this software in loop simulations, then you can go for discrete mode. It is easy for you to deploy that. So for the time being, let me go for ODE23TB. You can apply. Okay. And if you run this simulation, let me go to style. I want a white background. Now, if you run this, you're getting a proper switching frequency. But let us make the t again as 1 by 50. And if you run this, then you can actually see the waveform properly. Still the square wave is not proper. I think the waveform is still not proper. This is because, see, actually, whenever the, I think 1 minute. I'll make it as 1 by t itself. Yeah. Now, as you can see that it is going to compare, but again you got a pulse. If you see that for a lower one, you're getting an extra pulse. Photo style. Okay. Now I think you can see the waveform. So during this time, you again getting a small pulse. This is because whenever it is greater than that, it is going to trigger this. If you see this small time also, it is going to trigger, which is we have to avoid that. For that, we have to modify this to a bit extent. This is because whenever it is less than that, it is going to trigger. Whenever it is 0, this is going to be triggered again, which is we have to avoid that. For that, you have to compare whenever the signal is greater, whenever the signal is positive, whenever your reference wave is positive, then only S1 should respond. Whenever your signal is negative or carrier is negative, also reference is negative, then only S2 should respond. So let us type this as S2. Let us type this as S1. Now let us modify this logic. I'm going to copy this, Control C, Control V. I'm going to modify this logic. There is something called, 1 minute. So let us use the same relational operator. So we'll use something called greater. Let us give that as constant. For this constant, we'll make it 0. We'll give it here. The other one, we have to see this sine wave. Whenever this is less than 0, then it has to trigger only S1. So there is something called AND. Again, you can use logical operator. There is something called AND. Whenever it is greater than 0, it has to the output has to go to AND. At the same time, it should be greater than this. Not this one. It should be greater than this. So this condition should work to give S1. At the same time, it should be greater than 0 to give that pulse. So here, let us delete this. Or instead, I can give it S1 here. I can make it as a comment. Right click, comment out. You can delete this one. You can give this one here. At the same time, whenever this is less than 0, whenever my switching sequence is less than 0, again it has to be a condition here whenever it is less than 0, and whenever this condition works, it has to go to my S2. Right click, comment out. You can actually drag it, place it here. Okay, I'm going to comment this. I don't want that. So this I'm going to simulate now. Okay, now if you can see that I'm getting a proper thing in my S1 switch, whereas my S2 there is again a small glitch. Again, if you see this instant, after this it is going to observe this. This is because of this EPS signal. For that, even in hardware you may face that problem if you have this peak value here. In order to prevent that, instead of using this existing repeating sequence, you have to code it. That a code I'm going to give you now. There is something called MATLAB function. So for this one, let us use, there is something called manual switch. So this manual switch, you give it one to this one, the other one to triangular wave. So delete this. This you can give it here. See, you people can take the screenshots after the completion of this, and you can work out at a later stage. To the input of this, there is something called clock. Now I need to generate a triangular waveform like this. I need to generate a triangular waveform. I need to generate a triangular waveform like this. So it is not, it's like, so you have to do some coding for that. There is something called sine inverse. So using that command, you can do that. So I'm going to share it now. You can see in the chat box. You might receive some code in your chat box. Even I will get the same. So you can copy that. Control C. And you can place it here. Control V. See, what does this do is, I'm let us have switching frequency as 50 Hz itself. So let us have the switching frequency as 50. What it is going to do is, A sine is a sine inverse representation. Here by using sine function, it is going to give some value from between 0 to 1. I mean, from -1 to 1, it is going to vary with respect to time. Here, T is my triangular input. T is my triangular input. Let me save this. So which is nothing but clock. My input is clock here. My output is Y. Y is nothing but this triangular output. So you can save this, Control S. Then you can see that as a triangular. Now this is your MATLAB function. For this 50 Hz, I'm going to generate a triangular waveform. If you apply sine inverse, what we get is you'll get a sawtooth waveform. You'll get a sawtooth waveform like this. Even you can try it later. You'll get a sawtooth waveform like this. But we want a waveform like this. We want a waveform like this. But if you just do only this, code, then you will get a waveform like this. I mean a simple ramp and a straight line. Simple ramp and a straight line. Let's go to annotate. So if I do this simulation now, so I have connected here. Now let us do this simulation. Still we got this. This is because of square wave that we have here. I got this. Actually, it is not supposed to come. Okay, let us assume this why we got this. So whenever my triangular is greater than 0, sorry. So I'm detecting the peak whenever it is greater than 0, I'm getting this, or when it is less than 0, I'm getting this. So still it is a problem. Okay, we'll check this. So we have to replace this also with a code. I didn't. Okay, then we'll see that later. So if once you generate this sequence, once we generate this sequence, then the same thing you can give it there. We'll sort it out actually. Actually, it has to come from here, but I'm getting this again. So somewhere logic I have missed here. So whenever my signal is less than this, and at the same time, when it is not, okay. Whenever my signal is greater than this, okay, when it is not, and it has to compare with and, so you can give it to S2. Sorry, this is the problem I made. I have to connect it to this one. Now let us check the simulation. Yeah, we got it. So that is because of this sawtooth waveform. Because of that small segment only, you're getting this pulse. Either you will get it here or you'll get it here. By using this EPS, if I use plus EPS, you may get in S2. If I use EPS in T by 2, you may get it in S1. So, I mean, if you just make minus EPS here, by making T by 2 only here, that also can be done. But again, you will have that same pulse, an extra pulse in either of these things. In order to prevent that, we have to do coding instead of using this repeating sequence. This is only for single pulse width modulation, but most of the times this problem won't come here, as we are not going to use this square wave reference. Instead of that, we're going to use some other techniques like SPWM or SVPWM and all. So this is for single PWM. I think now you got the idea. So if you just give this, it is going to trigger that. Should I use this two sources for the time being? Wait, then. Okay, now I think we may get it. Later on, I am going to take this capacitance and I tell you. Still 0 to 2, it's constant. Okay, we'll see that. I mean, I can just tell you that how we can generate a sequence. Now, this is fine. As I said, we have this repeating sequence and we have square wave generator, but we are not getting a proper output. Then I told you to use this function. So this repeating sequence sometimes is not viable for implementation in hardware. So an alternative required, which is something code, you have to do that. Even in coding, you have to take some parameter, which is going to increment. You have to take some counter, which is going to increment all the time, which is your time, t. So a square wave generator is not a big difficult task for you. So this repeating sequence, I'm just going to give it an alternative. Like whenever this is greater, you just have to subtract that. So you'll have this. That means instead of this, you'll get this. At a later stage, it's going to give normally. So this is one part. If you just go to multiple PWM, I'm going to use the same concept. But if you see that in multiple PWM, all the pulses are of uniform width. Here also all the pulses are of uniform width. By comparing these two, you can generate the required signals. So let us do that. So in this triangular itself, let us do 50 Hz. Instead of 50, let us have some switching frequency. Let us take 50 into 4. So we'll get 4 pulses. Save it, Control S. And let us check the waveforms. If you observe this, I'm not getting the waveform properly. It is like it is actually comparing a different part of the waveform here. So again, you have to modify this code, which I'm going to give you now. Time. Why do we need infinite time there? So now I have given another code to you. You can try to copy that. So instead of this triangular, so instead of overwriting this, let us copy this. Control C. You can comment it so that it should not create any conflict. Control V. So here is your network. And you change anything here. So I have the code. I just gave you the code now. Control C. Control V. Okay. Now I have just used this 15 to 4. Instead of earlier one, it is like if you see the earlier code, we have used 1 minus y1 and minus 1 minus y1. Here I've just made it 1 plus 1, 1 plus y1. If you make it, then you'll get the thing properly. S. So this is also triangular. And let us see the pulses. We are getting a pulse waveform like this. Okay, now, yeah, I got it. Here, I'm always getting the pulses continuously in the positive direction. You have to write again a code. You have to further modify this so that whenever this is less than 0, this has to be multiplied with minus 1. So for this code, take it back. Now you have to take this code. Whenever it is, there is something called switch. If you type switch, go to foundation library, electrical and electrical elements. See here, foundation library, electrical element switch. not this, sorry, foundational training, which, yeah, this is a switch. This is first one itself you can take. For this one, this waveform has to go at once if the signal is greater than 0. If the signal is greater than 0, my signal has to go as it is. If not, it has to go by multiplying with -1. So let us delete this and let us give this output here. Here we have to connect a gain of -1. So let us drag it and place it here. So now let us see the waveforms. Yeah, I think we got it. So as I said, we're going to get this waveform, but we just need it to compare in the bottom leg. So you just have to compare this reference wave. You have to multiply it and you can compare this. This is one segment. I think you can get it right. Can you able to do this? I recommend you to take the screenshots of this. I have sent you the code of this one. I recommend you to take the screenshots of this. You can take some time to implement. Am I fast? No, it's fine. Thank you. Can you please show the sequence generator configuration? Means this one. Yeah, here it is. Yeah, I can take the screenshot. See, and I thought of telling one more thing. Here I have defined my T in command window. But if you open it again and you don't know what T value you have given, so it is again a difficult task to remember the T value again. So instead, in this simulation itself, you can go to right click, go to model properties. There is something called callbacks here in the initial function. So before starting this, you can type T is equal to whatever the thing that you want. Suppose if I want 1 by 50, you can just type 1 by 50 here itself and you can click apply. Okay. So whenever you reopen the simulation, this simulation will have the T value stored in this one itself. It won't be removed. But in workspace, whenever you open the MATLAB again and again, it will go vanished. You won't have any workspace here. So this is how you can generate the pulse. Once you generate the pulse, I think some connection problem I have made. So if you just cross check it, you may get it. But generation of pulse is a big issue. Once you generate the pulse, you can directly take this S1 and you can give it here. So it is going to generate as per that. So here we have completed single pulse with modulation and multiple pulse with modulation. What is the difference? It actually comes with, if you just see the harmonic content in this voltage waveform, then you'll get it. That we'll see in the next session. Because it's just a simple block only. I have to cross check it. Why it's not coming? So if I see the simulation, so it's almost 0 actually, it's 10 power minus 12. So you'll see that why it's giving 0. That means it's not at all properly triggering. So if I take S1, S2, okay, for the time being, we'll just learn this pulse width modulation methods. Then we can implement one after the other. It's somewhere with the circuit itself. We have to check for that. So this is multiple pulse width modulation. The next one is sinusoidal pulse width modulation. There is no much difference between multiple pulse and sinusoidal. Just replace square wave with sinusoidal wave. Here we have a square wave. Instead of that, I'm just going to use a sinusoidal wave here. So in this one, if you see that in a normal basic pulse width modulation, all the widths are equal in size. But if you see the sinusoidal pulses, you are going to have a variable pulses here. But it has some advantage if you just go for a higher switching frequency. You'll see that. So for sinusoidal signal, the same thing. Control C. We're going to comment this. Control V. So this is our signal. What we have to do is we have to remove the square wave generator and we have to use some sine wave generator. If you type sine, you'll get some sine wave generators. Don't go for lookup tables, use sine wave itself. So there is something called sine wave. For this, I'm going to use a modulation index 0.9. It is up to you. If you take this reference as 0 to 1, it has to be 0.9 somewhere. So by default, it is something radians per second. So it is not in hertz. So you have to make sure that it is written in radians. 2 pi f is the omega, but instead of f, you can write 2 pi by t. So t is your frequency, fundamental frequency. You can click apply. Okay. I think what is the t we have given in model properties? T is given as 1 by 50. Then we'll write it f equal to 1e4, which is 110 kilohertz switching frequency. We can click apply. So instead of 2 pi by t, let us go for 2 pi f. Apply. Okay. And let us see the waveform. I don't know how it is like. Somewhere I did mistake. Oh, sorry. For this, I have to give t itself. 2 pi by t. So, I mean, the sinusoidal signal should be our fundamental component. So if my fundamental component frequency is 50 hertz, then you have to give the same frequency here. So here in this repeating sequence, you can give whatever you want. Instead of t, let us make this 50 as 1e4. Or for the time being, let us use this itself. And let us simulate it. Now we may get it properly. I hope so. Yeah. Okay. My signal is initially negative. So whenever my signal is greater, it is going to give that variable pulse. Whenever my signal is smaller, I mean, whenever my signal is negative, it is going to trigger S2. So this is how we can do sinusoidal pulse width modulation. If you go for higher switching frequency, then your pulses will be more. But the disadvantage is your fundamental component will be reduced. If you see that, it is going to properly trigger that value. The line. You can actually see the things here. So at the exactly at these points, it is going to compare that. So this is how we can use sinusoidal pulse width modulation. So we have covered 3 topics. One is single pulse width modulation, multiple pulse width modulation, and sinusoidal pulse width modulation. There is something called selective harmonic elimination pulse width modulation. So what does it means? If you want to eliminate a specific harmonic contents, like suppose I want to eliminate third order 4, 5, 6, sorry, so 3, 5, 7, 9, and 11. If you want to eliminate 5 harmonics, then you can simply choose 5 angles to eliminate them. Suppose if I want to eliminate only one angle, I mean if I want to eliminate only the third harmonic, one angle is sufficient. If I want to eliminate 2 harmonics, that means 3 and 5, then you can use 2 angles. But if you have 5, if you want to eliminate top 5 harmonics, then you can choose 5 angles. But if you see that there are 5 angles that you want to choose, these angles in multiplication with this n, it might make this 0. So that alpha 1, whatever you choose that, it is going to make that harmonic content 0. But how to find this alpha 1, alpha 2 and all? It is always a big difficult task for us. So initially there is something called modulation index, which is your fundamental component to all other harmonics. So this modulation index, based on this, you're going to use the fundamental component, whatever the fundamental component that you want, that should be equal to this mi. And if you want to eliminate third, instead I want to eliminate third, instead of this n, use 3. That means the third harmonic components everywhere, it has to, all these sums you can actually use either plus minus like this, but it is not mandatory that you have to use minus only here. You can use all the times plus, that also can be done. This equation is up to you. These equations are up to you, but I have used this because I got that simulation. So now we have got these 5 angles, and you can see that this is again a matrix. If you see that cos alpha 1, cos alpha 2, there are 5 variables, I mean 5 things which are dependent on 5 variables, and you have 5 equations. In this one, the fundamental component value should be equal to mi. What about the rest? Rest of the signals should become 0. That means third harmonic, fifth, seventh, and ninth harmonics should become 0. But whereas your fundamental component, it should be equal to this value. So let us consider this in the form of matrix. In order to do this, in order to solve this, we are going to use Newton-Raphson method. SHE means selective harmonic elimination. So we're going to use Newton-Raphson method. I think most of you know that whatever the function that we have f, we're going to differentiate this with respect to that alpha, and whatever the initial value that we have, so this alpha we're going to add to that. Every time we're going to add to that, we're going to repeat this, and until this delta is almost negligible. Epsilon means it's almost negligible. That means I of alpha of I plus 1 is equal to alpha of I. If we do this, that means at this angle, if you substitute that angles, all these functions will become 0 and your fundamental component will become mi. Okay. So you have to assume some initial angles, alpha 1 to alpha 5, and initial modulation index we have to take 0. First we have to tune these parameters whatever we want, then we'll get angles. Okay, once we get these angles, how we can do the triggering, how to do that triggering sequence. So for this f, as you can see, as I told you, this f is cos alpha minus cos alpha 2 plus cos alpha 3, like this, and so on till cos alpha 5. So if you just see that at last cos 9 alpha 1 minus and so on, at last you get cos 9 alpha 5. See, this is one column matrix. Remember, this is not a square matrix. You cannot apply inverse transformation for a normal matrix. I mean, for a column matrix. So you have to give space. You have to take F as a column matrix only, and you have to define your variable df by d alpha, which is your function, that you have to write it in a form of square matrix, like minus sin alpha 1 space minus sin alpha 3 space sin alpha 2 and so on minus sin alpha 5, like this. So you have to make this manipulation. This is a 5 by 5 matrix. So once you differentiate this, if you inverse it, what is T here means T is this one. T is the matrix Mi 0 0 0. It is also a column matrix. It is this is F. So if we do that, we'll get this. So it is not so complex. We have to take the number of iterations to do this. So once we got this angle alpha 1 to alpha 5, then you have to take S1. Remember, this is a fixed one. It is not a pulse width modulation. Selective harmonic elimination, whatever the switching frequency, that whatever the fundamental frequency you have to take that as it is. So it's not like a higher switching frequency and all. So whenever between alpha 1 and alpha 2, your output should be high. At the same time, alpha 3 to alpha 4, your S1 should be high. So between alpha to 90, alpha 5 to 90, it should be high. Now you have to go in the back direction. So 180 minus alpha 5, alpha 4 to 180 minus alpha 3, like this you have to go. This is for switch 1. If you take the other one, it is from 0 to 180 degree. From 180 to 360 degree, so it has to be same thing. Everything you have to add 180 plus. Okay. So we'll do the same thing in simulation and we'll see that. So Control S. Let me save this and I'll try to open my SHV simulation. I think this one, right? Okay. See, if you just see my entire thing, I just have this PWM block. I have 4 switches, S1 to S4, and I have this, and I have made only these angles. So A1, A2. I never mentioned what is this A1 anywhere. But where you can get this A1, A2, here A1, A2 means alpha 1, alpha 2. You have to do coding before starting the simulation. First, you have to get this A1, A2 that optimized. This optimized value, we have to get this. Then you have to update here, and then only your system is going to simulate. So if I go to right click, if I see model properties, go to callbacks, initial function. Here you can see my code. See, first I'm going to eliminate 3, 5, 7 and 9th harmonics. As I said, you have to start from 0 to 1. You have to use all the modulation index range that you want, that you are operating. Now here is my iteration. Before starting that, you have to choose some angles, alpha 1 to alpha 5. At this time, remember, alpha 1 to alpha 5, whatever the angles that you are choosing, they should be in this sequence. So alpha 1 should be less than all the other angles. Alpha 2 should be less than all the above angles. So the angles should be in greater sequence and it should be in the range 0 to pi by 2 only. So that's what I have chosen. I have chosen some random angles 20, 30, 50, 70 and 80. These are my initial values because for the Newton-Raphson method, you have to give some initial values. Again, I made this iteration. This is my T function. As I said, first you have to choose that modulation index. So whatever the here M is between 0 to 1. This is a simple matrix. M is a matrix which is having 0 to 1, which almost have 100 values. Let us see that. If you type M equal to 0 is to 0.01 is to 1, if you enter, then it is a column matrix. If you just see that. So it's a matrix which are having an increments from 0 to 1 in the increment of 0.01. So it is just one column matrix. Sorry, one row matrix. For this one, if I want to choose any value in this, if I type m of 2, then I'll get this. Because the first one is 0, m of 2 is 0.01. If I choose m of 10, then it is going to give m of 10 as 0.09. So you have to choose a specific modulation to perform this matrix, to perform this Newton-Raphson. So, and this, from here itself, my simulation starts. For this one, I made I is 0 to 1 is to 1, sorry, 1 is to 101. Every time you have to choose one value. So for I, 1, that means for M1 of 1 means it's like M1 of 1, which is 0. So it is going to take my modulation index initially 0. Then it is going to perform this. So this is my f function. If you see this, this is just a column matrix. I have not given any spaces. If I give spaces, then it is like 2 columns. I didn't give any spaces. But if you see df, actually I have derivated this. So cos a1 you'll get minus sine a1, minus cos a2 you'll get plus sine a2. Everywhere I have if you see here, I have given space. So this is a square matrix. This df is a square matrix. Now here again, I want derivative of alpha, which is my df into t minus f. T minus f is my actual function. That means m1 minus of this. If you see here, if I take this entire thing onto the right hand side, so mi minus this entire term will become my first function. Similarly, 0, everything will become my second function. So these are my different functions that I have. So this is how I am getting. So every time alpha, you're going to use this alpha, whatever the alpha that I have got. This is my initial values. So I have already initiated them. This I have initiated here. Now this df, you received some derivative of a here. So this dA is nothing but your delta alpha. Now this you have to add it to initial angles. So here is my initial angle. So I have defined a matrix of alpha, which is a column matrix. If I mention quotation here means it is a column. So A1, A2, A3 will come like this. I can show you. If I type M equal to 1 colon 1 colon 1, that means it is a column. Yeah, so it is a column matrix. If I don't give column there, if I just give only space, then it will become a row matrix. See, now this is again a column matrix. For all these, I have added that. And again, see, I have taken very, very minute difference. Delta A, which is almost minus E minus 10 to minus 15. That means it's 10 power minus 15 angle, which is almost negligible. And that too, I have taken so many iterations. 1 is to 100. If you do this, you're going to have all A1, A2, and so on. I'm going to take another parameter to update this value in this, because they may overwrite the same thing. So it again starts from the basic. So I'm going to overwrite that and I'm going to use this. If you just let us make it as comment for the time being. We don't want this. Oh. So let us not see this apply. Okay. So I'm going to give this code, Control C, to your chat box. I think I have given it to you. You get that? Yeah, everyone. I think you didn't get the entire thing, right? Somewhere it got stopped. Wait. I'm giving everything. So rest of the code I'm giving it now. Okay, we'll see first whether we can simulate this or not. We don't want all that. Okay, click OK. See, what happens is whatever the code that I have written, it is going to simulate. And this, see, I need, as I said, whatever the fundamental frequency that I have, what this mod counter do is whenever it is greater than that, it is going to become 0. I think you know the mod function. Otherwise, it is going to give the signal as it is. That means it is going to give the reminder. Here clock is a basic increment which is going to increment like 0 to 0.2. This is my simulation time. Till that it is going to increment and it is going to compare. If you observe, all the angles that I have given are in what do you call, or angles. But if you see here, this is basically, it is giving in the range of 0 to 50, but I want in terms of 0 to 360. So I just have to divide this, and if I multiply with 360, it is going to vary from 0 to 360, 0 to 360, like that. So in that range, as I said, whenever my A1 is greater than that initial angle, omega t, you can tag this as omega t. So it should be greater than omega t, and it should be, I mean, between alpha 1 and alpha 2, omega t should be there, then it should go out. So similarly, between A2, A3 and A4, it should go out. Between A5 and 90, it should go out. Like 90 and A180 minus 5. This is how you can see that. This, you people can take 1 minute. Yeah, you people can take the screenshot. Because it is almost there. You can take this screenshot also. Take all. Yeah, this screenshot you can take. And you can do the same thing again on your own. But I'll give you the code. So if you do that, let us run the simulation. See, for the basic, first for the, what do you call, for the switch 1, it has to give this one. For switch 1 and switch 4, I have used 2 level, like switch 1 and switch 4. These two should be on at once, and switch 3 and switch 2 should be on at once. So for this one, whatever the output that I have got, it should go for S1 and S2. See, why I have used add means, in this one, only one case is going to come out. That means only one is going to become 1, the other will become 0. So at that time only you'll get 1. If you get 1 means your S1 and S4 will become 1. In the other case, it will become 0. So if you do that, I have made it in discrete mode. In discrete mode, I have used OD45 solver. See, in some solvers, you may not get the output. So you have to keep on changing the solvers and you have to check it. That is the only way. Sometimes you may not get it in OD45, you may get it in other way. So you have to cross check it and you can do that. So it's a simple resistance. So I've given 100 volt. If I run this simulation, do MATLAB. Okay. I think you can see that between alpha 1 to alpha 2, my output is high, and alpha 3, alpha 4, alpha 5, 90, something like this. So you can see the sequence and for 180 degrees. If you see that harmonic spectrum of this one, I think I have added, we can go to logging. So I have made it as half bridge, harmonic content, make use structure with time. Okay. I think some people cannot see in black screen. Is this black screen okay for you? So in this one, let us see whether the harmonic contents that we have are eliminated or not. If you go to discrete, go to preferences, tools, go to FFT analysis. Can you see the screen? My FFT analysis. I think you people are not seeing clear, so let me share this. Share my screen. I hope. I think you can see the FFT analysis now. So I have just used this. If you just, as I said, you have to go to discrete. You have to go to tools. You have to go to FFT analysis, and you can simulate that. Tools. If you click on FFT analysis, then you'll get this pop-up. Choose which signal that you want. If you just go for V inverter, choose your fundamental frequency 50. How many cycles you want? Whether one. If you have two, you can choose two also. That means it is going to choose for 2 cycles. And whether you want harmonic order or you want in hertz, you can choose harmonic order. You can click on compute FFT. If you see that, I have my fundamental one, my 3, 5, 7, 9. If you see, all those harmonic contents are eliminated in this selective harmonic elimination. So if you do this, even you can go for multiple things and you can choose that alpha properly. For this, they generally use it in HVDC systems because they'll use filters only for higher frequency terms. These can be easily eliminated if you can eliminate the higher order harmonics. This is one method of doing it. So this is one. I think you got this, how to do this selective harmonic elimination. Let me send you the code. Model properties, callbacks. Control C. We go to chart everyone. Control V. I think it's copying only segment by segment. Okay, let me copy. I'll copy it from here. I'll copy the main content along. Control C. Control V. So one segment was done. Okay, the next part. Till where it got. I think till this part it has done. So let us copy this extra part. Control C. Control V. Yeah. I think in 2 segments you got that. So you can do this simulation on your own. Shall I wait or shall I go to the next topic? See, why I have used this convert block means you cannot connect two different distinct signals. Like whatever this AND operation, they are actually the logical operators. That means they are binary. Either they will give 0 or 1. And this is not compatible with the normal 1, normal 0. So for that, there is something called convert. If you see data type conversion, in that by default it will have floor. Whether you want floor or even you can use ceiling, whatever you want. Floor, I generally use floor, and here int 32 I'll use. That is up to you. Whichever you want, you can use that. So by default it is inherit. So back propagation, it is going to understand that and it is going to give. So then you can actually add. So the binary values you cannot directly add there. So in order to add or whatever even you want to see in scope, you can in order to see in scope, you have to do this data type conversion. Suppose, let us see this, whether we can check the signal or not. If you go here and connect it here, this angle is actually a binary one. It is not converted. And this is signals or normal things. If I do the simulation, it is going to give errors. But this time it didn't give errors. How come? Okay, maybe this time it is compatible, but normally it is not going to compat. I mean, they are not going to be in compatible version. At the time you have to do this conversion. So this is your next topic is selective harmonic elimination PWM. So we have covered this one. The next one is space vector pulsate modulation. This is somewhat complex, but it is very interesting. So assume that I have a 3-leg inverter and you want to compare this. In this space vector, assume that there are 6 sections. If you just let us take this A. If I turn on Q1 with respect to pole, if I turn on Q1, my A will be equal to VDC. Similarly, if I give Q0 and Q4 1, my A will become 0. Do you remember the difference? So one is on, the other one has to be off in this one. It is not like earlier case. If one is on, the other one should not be off. If you see that in this case, where we can see that if S1 is on, in this case, S2 should not be responded here. It should not respond. This one should not respond. But in this case, for a 3-phase, by inherently, they are going to create the potential difference between the phases. So that is going to save us. So when Q1 is on, obviously the Q4 has to be off. Yeah, when Q1 is on, the Q2 has to be off. Okay. So when this is on, this one has to be off. There are 6 vectors. Suppose if this is on, means I'll consider it as 1. If this is off, means I'll consider it as 0. So when this is 1, obviously my Q4 has to be 0. And when Q1 is 0, obviously my Q4 has to be 1. See this to be in complement format. Similarly, Q3 can be either 1 or 0. This also can be either 1 or 0. Now if you see that I have 3 states or 3 legs in which if I give 1, 1, 1. Let me take A phase, B phase, C phase. If I'm giving only A phase 1 and Q3, Q5, 0, 0, that means Q6, Q2 are on. That means I'm giving only this as 1. That means my Q1 is connected to VDC. If I give Q3 0, Q4 0, then Q6 will be 1 and Q2 will be 1. That means my B is directly shorted and my C is directly shorted. That means this is 0, this is also 0. So these two are zeros, whereas my A, it is equal to VDC. This I am going to consider as 1, 0, 0. So this is my V1 vector. So how many possibilities we have? As we have 3 different bits. So we have 2 power. So 1, 0, 0, 0. We have so many vectors, like we have 2 power 3, which is nothing but 8 different possibilities. 8 different possibilities will have. So it is 0, 0, 0 to all ones. So 0, 0, 0 to all ones. Now, why we are going to discuss this vector? Assume that I just need a sinusoidal signal that starts from, it has to start from maximum. So Q1, I need a sinusoidal signal. So if I operate V1 and V2 between V1 and V2 continuously, that means if I give V1, it is going to give maximum. If I going to give V1, it is at maximum. Remember, this is not starting from 0, it is starting from maximum. That means it is going to start at 90 degree. This represents the 90 degrees for A phase. And this represents the 90 degrees for B phase. This represents the 90 degrees for C phase. So, but intermediately, if both this block, yeah. So if I'm going to turn both this one and this one on, so it is going to operate at this mode, like 1, 1 and 0. So these two are on. That means it is going to operate some angle at 60 degrees. If you see that, that means if these are equally triggered, that means this is continuously on, this is continuously on for some half time, then on an average, my signal will become V2. We'll see that in detail at a later stage. Let me stop this annotation. So as I said, we have 8 different possibilities. 100 means only this phase is on, the other two are grounded. 110, 010, like this. If you see that, if my V1 is 100, that means the entire A phase is at 90 degree maximum. If I give 010, entire B phase is at maximum. If I give 001, entire C phase is at maximum. So there are 3 maximums. If you observe, there are 2 possibilities here, 111 and 000. If I connect 111, if I connect this 1, 1 and 1, See, A, B, C, they are with respect to them, there is no potential difference. That means both with respect to ground, they may have some VDC, but with respect to A, B, C, the line potential is 0, isn't it? Similarly, if I give 0, 0, 0, all the three are shorted so that the potential difference among them is 0. So these two are called redundant values. If you see the potential difference, they are zeros. If you turn on all the three upper switches, if you turn on all the bottom lower switches, in both the cases, the voltage values between them is 0. That means they are directly shorted. There won't be potential difference across them. As I said, let us enter it into the concept. Suppose I have a switch, I have a source, I have a load. If I'm going to move this switch continuously, assume that this 10 volt and again 0 volt, 10 volt and 0 volt. Based on the time that I'm going to operate, that corresponding voltage is going to come here. If I have only one DC source, but you have two times, if you see that this is at one time, this is at one time. Obviously, when you can say that these two are 120-degree phase shift, we can say 120-degree phase shift when these two are at two different time instances. Similarly, here I have one vector and I have another vector. If I'm going to operate between 1, 0, 0 and 1, 1, 0, if I'm going to operate at between these two, it is going to operate at some random points. That means the resultant vector may be somewhere like this. Here, but in space vector modulation, they're going to trigger. If I start at V1, then I'll start V7, then I'll go to V2, and again I'll go to V1. So they are going to follow the sequence. Again, they'll go back. If you operate this, on an average, it is going to settle at some value at one time instant. If I'm going to increase the time t2, that means this vector will move towards this. If I'm going to increase t1, the vector will move towards this. If I keep on using this 0 all the time, which is nothing but t naught, then the matrix will have, it is going to reduce this magnitude. If I use between these two, it is going to have somewhere here between like this. But if I operate this if I'm going to operate V7 or V8, obviously I'm going to operate 0 value. That means its magnitude is going to decrease. So this is how we're going to operate here. That means instead of just one source, we have different switches that are going to operate at different times. Then the resultant vector at a different time may have a different voltage value. I think you got this right. And how we are going to perform this means this TS is your switching frequency. Whatever your fundamental, whatever your switching frequency is there, this TS is the switching frequency. And this V reference is what my instant of time. At what time I need this. That means this is a variable. This is going to move accordingly. So if I see T1 V1, T2 V2, and so on, T01 and T01, see these two is same, but at once I'm going to turn on all ones. The other time I'm going to turn on all zeros. That means I'll use upper switches at one time. I'll use lower switches at one time. This is because if I use only 111 to make 0 voltage value, then these are underutilized and these are overstressed. Q1, Q3, Q5 will be overstressed and Q4, Q6, Q2 will be underutilized. So I'm going to use both the states. That means V7 and V8. That means 111 or 000. You can use any of these states. How we can do this? Suppose assume that, and again you have to operate, in order to operate between these two, you should identify the sector. There is something called sector identification. Suppose if we take 0 to 360 degree, If I take 0 to 360 degree, suppose this is 360, it starts from 0. Between 0 and 1, I mean between 0 and 60 degree, I'm going to say it as sector 1. Assume that I have identified the sector. At that time, only these two vectors along with V7 and V8, it should operate. See, between these two vectors along with V7 and V8, it's going to operate. If it is sector 2, it has to operate between V2, V3, V7 and V8. It is not V0, it is V7. Here the concept may be difficult, but once you implement this, then it is easy for you to go for the next stages. So it is like between, I'm going to operate 111 first, then I'll go for 110, then I'll go for 010, and again I'll come back to 000. If I'm going to operate this based on the time T1 and T2, here based on the operating time T1, T2 and T0, this vector is going to start. If I'm going to increase, if I'm going to initially, I'll have initially I will have T1 more, and I will have T2 more, and I will have T2 less at this time. So it will have a vector more aligned to here. If I'm increasing this, then this vector is going to reduce because it is zero vector, right? So the potential difference will become 0. Smaller pencil. Okay. Okay. Suppose if I'm going to operate V2 for some time, then my vector will be more close to this. If I am operating, this T1 is larger. So slowly what I do is I'm going to reduce this T1 and I'm going to increase this T2. Then this vector will slowly move like this. So I'm going to have an appropriate 000 operation, which is my T0. Actually, this T0 is going to adjust my modulation index. If you don't want the full vector, if you want a partial vector, then you have to choose this properly, this T0 based on that. So if I want a smaller value, that means if modulation index is quite less, then this T0 will increase, so that you will have a smaller magnitude here. You will have a smaller magnitude. Even if you just even increase it, you will even have a smaller magnitude. If you keep on increasing, you will have a smaller magnitude. I mean, if your modulation index is reduced, that means this you're operating more 0 times, then you will have less potential difference. And with respect to operation, first you have to identify the sector. So which sector you want, that you have to choose. Which sector you want. If it is in sector 1, if it is sector 1, it has to operate between V1 and V2. If it is sector 2, it has to be operated between V2 and V3. Only these are going to change, but not only these are going to change, but not the times. Suppose this T1, they are going to be fixed over an entire cycle. Now how I'm going to trigger this? Assume that 000, there are 8 different states we have. 0, 0, V0, V1, V2, and so on till this is V8. You can say this with respect to me, this is V7 and V8. This is V8 and this is V7. Sorry. This is V7 because it is all ones. This is V7. This is V8. If you see these, there are 3 phases, VA, VB, VC. What I'm going to do is, for some time, I'm going to make all 0. Assume that I have identified my sector between 0 and 60 degrees. This is my initial angle. You have to choose this. So if I want between 0 and 60, how my switching pattern will be, for some small time, for t naught by 4, I'll make 0 0 0, then 1 0 0, 1 1 0, 1 1 1, like this. As I said, see, this is V1, which is 1 0 0. So this is my V2, which is 1 1 0, and the third one is either 0 0 0 or 1 1 1. 1 1 1. So it has to operate. If it starts from 0 0 0, then it has to go to 0 1 0 0, 0 0 0 to 1 0 0 for some time. Then again it will move to 1 1 0. For 1 1 0, it is going to operate for some time. Again it will go to 1 1 1 for the effective switch utilization. Then again it will go back to, now it will, once it is rotating in anti-clockwise, now you have to go it in clockwise. So after 1 1 0, it again will choose 1 1 0 and 1 0 0 and 0 0 0. That means after 1 1 1, 1 1 0 and again 1 0 0, again 0 0 0. This is how you're going to operate. If you see this, at this time, all the phases are 0 initially, then VA is going to become 1 0 0, whereas the other two phases are 0. After some time, my B phase is on. After some time, my C phase is on. If you observe that, my A phase, I'm going to apply maximum time. I'm going to give maximum value. That means at some point, it is going to have a maximum instant in sector 1. So obviously, it is going to have maximum here. In sector 1, it is more close to this. So VAN will be more. If you see sector 2, my sector 2 is between, V2 and V3. This is my sector 2. If you see here, I have identified 1, 2, 3, 4, 5, 6. Now it is in sector 2. Assume that I have identified my sector number, which is 2. Now it has to operate 1 1 0, 0, sorry, 0 0 0, 1 1 0, 0 1 0, again 1 1 1. You have to go back like this. So 1 1 1, sorry, 0 0 0, 1 1 0, 1 1 1, again come back to 1 1 1. You have to go again reverse now. 0 0 0, 1 1 1, like this. The sequence is normal and you have to know how long you have to turn on that. Is it clear or is it confusing? Okay, at the time of simulation you will understand. I think till now you got it right. First you have to identify your sector. Then in that sector, what is the sequence you have to follow? Suppose this is the sequence I have to follow. 0 0 to like this in sector 1, and each this you have to give. And after, so 0 0 0 for this time, like this you have to give. Once after this sector identification is done, obviously it is going to move to sector 2, and at this time this sequence is going to change now. The sequence is changing. Similarly, it will go for sector 3, sector 4 and so on. It will have a different sequence. I think you know how to generate the sequence. You know how to make this time selection. You know how to identify the sector. If you make all these three in a proper sequence, then you can get it. Let us see the process now. So what we have to see, first we have to generate some reference sinusoidal signals. If you see this sinusoidal signal, that means it is going to create, from this I'm going to identify the angle, instant of angle. So this is my reference signal, maybe it is 90 or there is like 60 or there is 30, 150 and so on. So you have to give some reference sinusoidal signals. Why three signals here means I have three phases. I have three phases. So I'm going to generate three sinusoidal signals here. Now what I do is I convert this three sinusoidal signals ABC to DQ reference frame. I think some of you might be knowing that, some of you might not know. What is that ABC to DQ reference means? If you take normal ABC vector representation like this, if you take ABC vector representation A, B and C, so what happens? These are going to rotate with respect to time. That means this maximum phase is going to become 0 and again it is going to come. It is going to, like, it will have maximum at one instant, then it will become 0 and it will go in this direction. It will go minus A. Similarly, at some time B will be there, and let us see at one instant of sinusoidal signals. I don't know whether I have them. Okay, we'll see at the time. What is this ABC to reference means? This A, B, C, with respect to time, if you take A is maximum now, B and C can be of somewhere in the middle. They will be half of that. Because if you take the sinusoidal signal as part of this overlapping, so if you take when A is maximum, B and C are half. Suppose this is A and this is B and this is C. So when A is maximum, B and C are half. That means they are actually displaced by 120 degree. Suppose when A is maximum, what happens to B and C? They must be half of their maximum values. This is at one instant. After some time, what happens? B will become maximum and A and B will become only, A and C will become only half of that. So what happens every time, though they are being displaced by 120 degrees, they are going to have a variable magnitude. It is difficult for us to do this analysis for that. So they do some matrix manipulations like this. So what I have here, A, B, sorry, actually it's this tool is not properly allowing me to write. So this is ABC. So these are variable vectors now. So if I take theta separately from them, so these DQ references, what happens is they're going to have a constant magnitude all the time, like D, Q, but they are going to rotate. That means this fixed line is going to move here, and this fixed line is going to move here. So this is like a, what do you call, stationary reference frame. If you take this, actually this has to be alpha beta frame. I just made only matrix calculations. That means instead of 3 vectors, I'm going to use only 2 vectors which are perpendicular by doing some matrix manipulations. This is alpha, this is beta. This I can do by using some matrix manipulations. These two are always 90 degrees with respect to each other. Now see, alpha and beta, what happens is they are going to vary with respect to time. Alpha, if assume that it is maximum at one point and later on it is going to reduce. It is going to reduce. Similarly, beta, at one point it is maximum. After some time it is going to reduce. But these two will have 90 degrees phase shift. These 3 phases we are going to convert into 2-phase representation. If you get only 2 phases, assume that I have alpha plus j beta. Alpha plus j beta. Now, you know that alpha is varying, beta is also varying. In order to find the magnitude, you'll do this thing like alpha square plus beta square, alpha square and beta square. But if you want time, if you want theta, it is simply tan inverse beta by alpha, imaginary by real. So what happens every time alpha beta are going to vary? So what happens? Your theta is going to vary. So here I'm going to identify my theta. Theta means if I find theta, if the theta is between 0 and 60 degree, then I'm going to define it as sector 1. If my sector is identified, I know the sequence of pulses that I have to operate. If you see any lot of textbooks, they have this derivation, how much this T1, how much this T2, and how much this T0 has to be. So these derivations are there, where here Sn is nothing but the sector number. Based on the sector, you have to do these operations. See, if you observe, my T0 is actually by 2 because I have only T0, but this is shared between 111 and 000. Both are making the output 0 vectors. So the entire T0 for half time I'm going to give for 111. The other half I'm going to give for 000. So once you identify, now you know the sector, you know the time, you know the sequence, it is easy for you to implement that. So once you know the sequence, you generate the pulses accordingly. So generating the pulses based on the time instances. See now, this is my sequence. Let us assume a three-dimensional array. I'm going to define an array. That means one is leg, time, and sector. Let us see here. Let us show it in. So if you take a three-dimensional vector like this, so let me take A is equal to rand of 1, 3, 6 like this. Or let us take 2, 3, 6. If you take this, what happens is it is actually three-dimensional vector. So for 001, it is going to create a 6 by 6 matrix like this. So it's like a 3 by 3. You have what you call, you have 6 matrices, out of which you're having a 2 by 3. That means you're having 6 elements in each thing. That means 2 rows and 3 columns. Like this, 6 variants. Among this, I'm going to choose leg, time instant, and sector. So what is that leg? I have 3 legs here because it is 3 phase. And how many sectors I may have? The next one is time instant. How many times I have? So this is actually my time instant. So I have 3 time instances, whether it is in T0 by 4 instant or T1 instant or T2 instant like this. So initially I'm going to take TA. It is T0 by 4 initially. Then you have to add time for this. So you have to add T1 by 2. It's actually not T1. It is T1 by 2. So this is T1 by 2. This is also T2 by 2. It is T2 by 2 and T1 by 2. So first you go at this time, what you're going to generate, you're going to give a matrix 0, 0, 0 for A, B, C. After some time, you're going to add a time T1 for that. So you're going to add T1 by 2. So for this time, it is going to give 1, 0, 0. But how you are going to detect this? So to detect this, we're going to use a sawtooth waveform. I think the theory is somewhat complex. To some extent, I think you understand. First, you have to identify your sector. Once you identify your sector, there is a three-dimensional array like this, and each time instant, you have a specific vector of this sequence. See here, 0, 0, 0 means A phase, B phase, and C phase. If you give 0, 0, 0 for ABC phase, that means all three switches are down off, or all the three switches should become 0. That means S1, S2, S3 should become, sorry, S1, S3 and S5, they should be off, which are upper leg switches. These are upper leg switches. So these should be open, and all the bottom leg switches should be shorted. So you have to detect the sequence. Now I have identified my sector, and I have to take this sequence based on the time. Next time I'll go for this. After some time I'll go for this. By comparing this with the sawtooth waveform, I'm going to get this. We'll see that everything at the time of simulation. Okay. So this is space vector modulation. Shall we see it now, or shall we see it tomorrow morning? Tomorrow? Anyone can respond through chat. Am I clear on this? I think space vector pulse width modulation, you got it right. You're going to operate. You have some different sectors, and based on the sector, you're going to operate this on an average. And based on that average value, it is going to operate at a specific time. Based on that specific time, in order to operate that, you should follow a sequence. You should follow a sequence. But in order to follow that sequence, for how long you have to follow each switch? For how long you have to follow this? How long you have to follow this? So based on that, in that sector, it is going to create a vector like this. It is going to complete that circle. So how the sector is chosen? As I said here, I think you know to generate a sinusoidal signals, right? You have a sinusoidal signal. As I said, I have three-phase sinusoidal signals. So I'll do some conversion here. ABC to DQ conversion will be there. From that, I'm going to find theta. If I find theta, there is something called clock, which is nothing but my omega t. If it is between 0 and 60, you have to make this as sector 1. That means that Sn value should become 1. This Sn value should become 1. So once you know Sn, then you can identify this 3 times. Once you know the 3 times, you can know, for which time, which sequence has to be done. So that is why I took one matrix representation. Then we'll see this. I think we'll see tomorrow. Initially, we'll start this. Then we'll go for a hysteresis current controller and multi-level inverters. Any queries so far? This we'll see in the tomorrow morning. I'll go a bit fast. You can read the concept of this space vector modulation once again, and you can do this analysis. What do you call it? Then we'll simulate this, and I'll give you the segment of code of that, and you can do this. Wherever I'm saying that to take you the screenshots, I recommend you to take the screenshots. The files are not going to be given. If you have any queries, you can raise hand so that there is something raise hand for you. From where we should study theoretical part. There are some videos explained by NPTL, I mean ISC Bangalore, Chakravarti sir, there is one faculty. You can see ISC Bangalore NPTL SVPWM. If you search it, is going to explain the concept in a brief way. Then after seeing my simulation, you'll get the clear idea on how can you do for two-level inverter. This is actually for two-level inverter only. For multi-level inverters, this time instances is going to split again. And here you have only two levels, that means 0 and 1. Whereas in multi-level inverters, you have 3 levels. Suppose if it is a 3 level, you have -1, 0 and 1. If it is 5 levels, -2, -1, 0, 1 and -1. Sorry, 0, 1 and 2. So this is how you'll have number of levels. So this time is going to split. And even there is internal sectors. This matrix is going to expand actually. It is not just a 3 by 3 matrix. It will be a 5 by 5 matrix. So here it's like 3-dimensional array, right? So instead of this 3-dimensional array, we'll go for 5-dimensional array and all. That we'll see in tomorrow's class. Any other queries? But space vector modulation is more advantageous compared to sinusoidal PWM because this one is going to give 1.5 times higher fundamental component than sinusoidal pulse width modulation. If you use sinusoidal pulse width modulation, it's something like it will go for something 2 by root 3 something. Here you'll get 1 by root 2 times. If you compare that, the fundamental component will be more in SVPWM than SPWM. That means sinusoidal PWM. So instead of this is what I'm saying. Instead of this, you'll have more fundamental component there. Okay. That's it for today's session. The time is up. Then we'll see the rest of the session tomorrow, and we'll go for the next sessions at a later stage. Thank you. If you have any queries, you can post your queries in the chat box. This chat box will be downloaded to you. I think so. In your documents somewhere in some location, it will be downloaded. I think even you can also download this chart. There is some option, but if you check it, you'll get it. Or you can simply copy the chart and you can keep it. If you have any other queries, you can ask for it. Okay. Okay, thank you. Thank you. I think you got some idea how to start this thing. We'll see in the next session. Thank you.